Okay, so 1.5 deals with analyzing graphs of functions. A lot of it goes along with what we did yesterday in 1.3 and the day before in 1.1/1.2, and you'll see some of the slides are kind of repeats of what we've seen before. So example 1, finding the domain and range of a function. We just did this. So we use the graph of a function f to show in figure 1.34 to find the domain of f, the function values when f of -1 and f of 2, and the range of the function. So our domain, we go from left to right. We have a closed circle all the way to the left, so that means we have a bracket to start off our domain. And our smallest x value here would be -1. And our largest x value is 5. But since we have an open circle, this means we end our domain with a parentheses.
Miss Carver?
Yes. Oh, I'm not...
I don't know if you meant to or not, but you're not screen sharing.
Thank you. And then lastly, we need to find the range. So range, we start at the bottom and go to the top of our graph. The lowest y value is -3. And then the highest y value is 3. Any questions here? Yeah, you always start at the lowest. For both domain and range, you always start at the lowest value, the smallest value of our graph, and then we go to the biggest value. Any questions here? Okay, next we have the graph of a function. We use the use of dots open or closed at the extreme left and right points of a graph indicate that the graph does not extend beyond these points. If such dots are not on the graph, then assume that the graph extends beyond these points. So here we see that since this is a closed dot, our graph ends there. Since this is an open dot, our graph ends there, but we just need to know that the open dot means that it doesn't include that 5. So it's all values less than 5, just not including that 5. If we didn't have those dots, then we would just assume that our graph would be an arrow and goes on forever. Next we have the zeros of a function. If the graph of a function x has an x-intercept at a, 0, then a is a 0 of the graph. So our x is going to be some number when our y is equal to 0. So the zeros of a function f of x are the x values for which f of x is equal to 0. So to find our zeros of our graph, we set our y equal to 0. We're going to do some examples on the next page. So we need to find the zeros of each function. So we change our f of x to be 0. And then we just solve for x. So we have 0 is equal to 3x squared plus x minus 10. Now we just need to find our factors. So two numbers. What we do when we have a number in front of x is multiply the first and the last number together. So this would be -30. And then we need two factors of -30 that add and give us a +1. So what would two factors of -30 be that give us a +1?
6 and -5.
Awesome, 6 and -5. So we're going to put 6 and -5 into our parentheses down here. So we have x plus 6 and x minus 5. But we can't forget about this 3 out front, so what we do is divide both of these by 3, so we divide our numbers here by 3. If it goes in evenly, we simplify it. So we have x plus 6 over 3. 6 over 3 simplifies to 2, so we just change this to x plus 2. If it does not go in evenly, if we cannot simplify it, we move it to the front. So this becomes 3x minus 5. So now we set both pieces equal to 0. So we're going to do x plus 2 is equal to 0, and 3x minus 5 is equal to 0. And then just find our two values for x. So for our first equation, we just subtract 2 on each side, so we have x is equal to negative 2. Our second equation, we need to add 5 to both sides, and then we divide both sides by 3. So we get x is equal to 5/3. So our two zeros of our graph here are going to be negative 2 and 5/3. When factoring this, since we started with a number in front of x, so since our number in front of x was not 1, we had to multiply the first and the last terms together, find our two factors of those terms, and put them into our parentheses, and then we take our first term, which we said was 3, and divide both of our numbers by that 3. If it doesn't go in evenly, then we need to move it to the front in front of x.
Okay, got it.
Remember, if you wanted to show that or just confirm with yourself, check with yourself to see if you did it right, you can always FOIL this back out to see if you get the original. So that's one way you can check your work. Or you can take your two answers that you found and plug them back into x. And then you would get 0, which was our goal. Okay, let's go on to b. So we're doing the same thing here. We're changing that g of x to 0. So we have 0 is equal to the square root of 10 minus x squared. We need to get x all by itself, so we're going to perform inverse operations. So since we're square rooting the right side, to get rid of that, we need to square both sides. 0 squared is just 0. And the square root and the squared cancel out. So we're left with 0 is equal to 10 minus x squared. To get x all by itself, I'm going to add x squared to both sides. So we have x squared is equal to 10. And then I just need to take the square root of both sides to get rid of that x squared, or the squared on the x. So I'm left with x is equal to the square root of 10. So our 0 for this is square root of 10. For c, when we have a fraction, we know our fraction equals 0 when the numerator is 0. So for this one, all we have to do is take our numerator and set it equal to 0. So we have 2t minus 3 is equal to 0. Now we just solve for t, so we're going to add 3 to both sides. So we have 2t is equal to 3. And then we just divide 2. So t is equal to 3 halves. So our 0 for this function is 3 halves. Any questions here?
Wait, Miss Carver, would you do the same thing to the bottom too, or no?
Nope.
You just leave.
When you have a fraction, if the top is 0, the whole fraction's 0. If you have 0 over 100, this is equal to 0. 0 over
yeah.
2 is equal to
Oh,
0.
that's right.
So it doesn't matter what the bottom is, so we don't have to do anything with the bottom.
Yeah, just do the top. Okay. Thank you.
Do we
Miss Carver,
always
that-
start at the top?
For a fraction, yes. Fractions, all you have to do is set the top equal to 0, and that's it. You can ignore the bottom.
Miss Carver, that's a plus sign, right? Like a plus sign.
Where?
Like the plus equals to 3 over.
That's a t, because we start with a
Oh, a
t.
t.
Yeah, instead of x, it gave us t for this one.
Sorry. Sorry.
No problem. Okay, this next slide we've definitely seen before. Use the graphs to describe the increasing, decreasing, or constant behavior of each graph. And you guys, I know you know how to do this. So what would our interval be for increasing for this graph?
Like negative 1.3 to
So
0.2.
for
Negative 0.
For this one, we would assume that these have arrows on them, that it goes on forever because it doesn't have that closed circle.
Oh, so it'd just
Infinity?
be all real numbers.
Yep, all real numbers. So we could put all real numbers or negative infinity to infinity. What would our interval of decreasing be?
All real numbers.
Does our graph decrease at all?
Oh yeah. Right. It's like, oh wait, no, it doesn't.
No, it doesn't. So we don't have an interval of decreasing. So it just doesn't decrease. So we don't need to put anything. All right, for B, what would our interval of increasing be?
It would be negative infinity to negative 1.
Awesome. Negative infinity to negative 1, because we increase until we get to this point. Do we have another interval of increasing here?
Yeah, from 1 to infinity.
Awesome, from 1 to infinity. And then what would our interval of decreasing be?
Negative 1 to 1.
Perfect. So we're decreasing from this point to this point, so that would be negative 1 to 1. Okay, for C, what's our interval of increasing?
Negative infinity to 0.
Awesome. Negative infinity to 0. What about our interval of decreasing?
2 to infinity.
Perfect. 2 to infinity. And then our constant interval?
From 0 to 2.
Perfect. 0 to 2. Any questions here?
Miss Carver,
Yes.
for the decreasing, why wouldn't it be 2 to negative infinity instead of regular infinity?
Because we're looking at, that's a good question, we're looking at our x values here. So our x is just getting bigger and bigger as we go this way. So it's from 2 to positive infinity because we're going in that right direction with bigger numbers.
Oh, I got it. Thank you.
Okay, next slide. Again, this one's a repeat. We have our relative max and min. So it shows the graph shows several different examples of relative min and relative max. So we know that our max is always going to be the tippy top points here, and then the relative min is always our little valleys that we have in here.
That out, if that was a question on the quiz.
Yep.
Okay.
So we haven't made the quiz yet, but it would typically ask you if there are any max or mins. So here we would have a relative max, and then we would just name this point. So if this was like 1, 2, we would have a relative max or relative min at the point 1, 2. So you would just say where the relative min and relative max are.
Okay, thank you. But we just have to point.
Okay, next slide. We have the average. Yep.
Sorry to interrupt you.
So this only applies for the curvy graphs?
Yep.
Okay. Thank you.
Okay, next we have even and odd functions. So a function is said to be even when its graph is symmetric with respect to the y-axis, and a function is odd when its graph is symmetric with respect to the origin. So the symmetry test yields the following tests for even and odd functions. So a function y is equal to f of x is even for each x in the domain of f when we plug in negative x and get x. So looking at the bottom part here, it's even if we take f of x, make x negative, and we end up with our original function. And then it's odd if we plug in a negative x and get the negative version of our function. We're going to do some examples, which it's easier to explain once we do examples. So when you take x and plug in negative x, if you get the original function, then you have an even function. If you take x and plug in a negative x and get the negative version of the function, then it is an odd function. So in our example here, the function g of x is equal to x cubed minus x is odd because when we plug in x, we get the negative version of our function. So let's plug in a negative x and see what we get. So we take all of our x's in this equation and plug in a negative x. So we have g of negative x is equal to, we have a negative x cubed minus negative x. And now we just simplify. Negative x cubed would be negative x cubed. And a negative minus a negative x would be a plus x. So if we took our original g of x equation and multiplied everything by a negative, we would end up with negative x cubed plus x. So since g of negative x is equal to the negative g of x, then this would be an odd function. Okay, let's take a look at another example like this one. So the function h of x is equal to x squared plus 1 is even because h of negative x is equal to h of x. So this is saying when we plug in a negative x for all of our x's, we're going to end up with our original function. So if we plug in negative x into x, negative x squared is going to be a positive x squared plus 1. So we end up with our original function, which makes this even. Another way we can test for even and odd functions is if we plug in a number and its opposite, if we get the same answer, then it's an even function. If we get opposite answers, so opposite meaning if it was like, if we got 8 and negative 8, so a number and its opposite would be its negative. So if we got opposite answers, then they would be odd functions. And then if we got different answers, then it's neither. So for this one, if we tried it using this method where we plug in a number and its opposite, we can plug in any number that is greater than 1. So let's plug in 2 and negative 2. So we're going to plug in h of 2 and h of negative 2. When we plug in h of 2, we get 2 squared plus 1. 2 squared is 4, plus 1 would be 5. When we plug in negative 2, we get negative 2 squared plus 1. Negative 2 squared is 4, plus 1 would be 5. So we get the same answer, so this would mean that this is an even function. So this is the algebraic way to solve it, but this is kind of like a shortcut trick to solve it, which I think plugging in a number and its opposite is a bit easier. It's kind of less confusing. We can also tell if we have even or odd functions just by the graphs. So we said an even function is symmetric with respect to the y-axis, and an odd function is symmetric with respect to the origin. And that means you can just flip the graph upside down. Like if you just take your graph and flip it upside down, the graph looks exactly the same. So looking at our first graph, we know it's not symmetric with respect to the y-axis because then it would look like this. So it's not even. To check and see if it's odd, we need to see if it's symmetric with respect to the origin. So we could just flip it upside down and we would get the same thing. So this is an odd function. In our second example, we see that this is symmetric with respect to the y-axis, so this would be an even function. Any questions here?
So for the odd one, you just have to connect the line, like not really, but hypothetically connect the two dots to see if it's symmetric across the origin.
Not really. So to see if it's symmetric across the origin, the best thing to do would just be to literally take your graph and then just flip it upside down and see if you get the same graph.
Okay.
Okay, we have one last slide. So we need to tell whether these are even, odd, or neither. So looking at number 1, we're going to plug in a number and its opposite. So what number should we plug in? Anybody? Give me a number.
3.
Let's pick 2 just because that's easier to work with.
Alright.
Especially when we're cubing it, the smaller numbers are just better. So we're going to plug in 2 and negative 2. So when we plug in 2, we get 2 cubed minus 6 times 2. 2 cubed is 8. 6 times 2 is 12, so 8 minus 12 would be negative 4. Now we plug in negative 2. We have negative 2 cubed minus 6 times negative 2. Negative 2 cubed is negative 8. And negative 6 times negative 2 is positive 12. Negative 8 plus 12 is positive 4. So since we got opposites here, we got negative 4 and a positive 4, that means that this is an odd function. Let's take a look at number 2. Again, let's plug in 2 and negative 2. So we have 2 to the 4th power minus 2 times x to the 3rd power. 2 to the 4th power would be 16 minus 2 times x to the 3rd power, which would be 8. So we got 16 minus 16, which is 0. Now we plug in negative 2, and we get negative 2 to the 4th power minus 2 times negative 2 to the 3rd power. Negative 2 to the 4th power would be 16. Negative 2 to the 3rd power is negative 8, and negative 8 times negative 2 would be positive 16.
Miss Carver,
Yes.
you didn't plug in for the 2 in the first one, like for positive 2? No, I'm sorry, for the second one. Like, I'm talking about, like, aren't you supposed to plug in 2 also in that x cubed?
Yeah. I plugged it in my head, like I did 2
Oh, okay,
cubed,
okay.
but I'm sorry. Yeah, you're right. Okay, so then we get 16 plus 16, which is 32. So we get different answers here. So would this be even, odd, or neither?
Neither.
Neither. For here, the number 3, this is supposed to be x squared plus 2x plus 1. It kind of got cut off on the last page. But again, we're going to plug in 2 and negative 2 and see what we get. So we have 2 squared plus 2 times 2 plus 1. And then we plug in negative 2, we have negative 2 squared plus 2 times negative 2 plus 1. So 2 squared would be 4, plus 2 times 2 is 4, plus 1. This would give us 9. And then we have negative 2 squared, which is 4. 2 times negative 2 would be negative 4, plus 1, so this would be 1. So we get different answers. Is this even, odd, or neither?
Either.
Neither. Let's go to number 4. Again, we're going to plug in 2 and negative 2. We get 2 squared plus 6, which is 4 plus 6, so we get 10. Then we have negative 2 squared plus 6, which is 4 plus 6 and 10. So we get the same answer. Is this even, odd, or neither?
Even. I mean, yeah, even.
Even. Yes. Number 5. Again, we plug in 2 and negative 2. We have 2 times 2 cubed plus 7. So this would be 816 plus 7, which is 23. And then for g of negative 2, we have 2. We plug in negative 2 cubed plus 7. Negative 2 cubed would be negative 8 times 2 would be negative 16 plus 7, and we get negative 9. So we get different answers. Are these even, odd, or neither?
Neither.
Neither. All right, and then looking at our graphs real quick. Number 6, is this symmetric with respect to the y-axis or with respect to the origin, or neither?
Y-axis.
The y-axis. So is this even, odd, or neither? Even. What about number 7?
Not symmetrical.
Not symmetrical. So would this be even, odd, or neither? Neither. And then number 8?
Odd.
Odd.
Odd. Awesome. So that's it for the notes.